The group of elements known as the actinide series is at the very bottom of the periodic table. The actinides share some properties with the transition metals, including high melting and boiling points. However, they are all radioactive, and most are artificial, which makes them unique among all the groups in the periodic table. Although these elements are a subseries of the transition metals, their group has often been considered separately. The actinide series generally includes the 15 elements from actinium to lawrencium. All actinides heavier than uranium are artificially produced, either in a laboratory or as a byproduct of nuclear reactions. Most of the actinides weren't discovered until the 20th century, when technology allowed scientists to create the environments necessary to produce and detect these elements. All the actinides are radioactive. Uranium and plutonium are probably the best known of the series. They gained worldwide recognition as the key components of the atomic bombs dropped on Japan at the end of World War II, and are still vital for nuclear weapons today. But radioactivity can also be beneficial. The actinides are commonly used in cancer treatments and as an efficient heat and power source. The radioactivity of the actinides can be explained by taking a closer look at the periodic table. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. The actinide series is entirely in period 7, meaning that every atom has 7 electron shells. The electrons in this outermost shell are called valence electrons. It takes 8 valence electrons to fill an outermost electron shell and make an atom stable. The elements are listed in order of their atomic number, which represents the number of protons in an element's nucleus. In an element's normal or ground state, the number of protons in the nucleus is equal to the number of electrons in the shells. The radioactivity of the actinides stems from the nucleus. This is why applications that use radioactivity are described as nuclear. The elements in the actinide series are some of the heaviest elements in the universe, so they have very high atomic numbers. The nuclei of these atoms are so big that normal atomic forces can't hold them together, and they become unstable. The nucleus releases matter and energy in an attempt to gain stability. When this happens, the atom changes or transmutes into a completely new element in a process called radioactive decay. There are several types of decay, each releasing a different form of radiation. Alpha particles are the most common form of radiation in the actinide series. An alpha particle is the same as a helium nucleus with 2 neutrons and 2 protons. When an element undergoes alpha decay, it turns into a new element with 2 fewer protons. For example, americium-241 has 95 protons and 146 neutrons. It experiences alpha decay and becomes neptunium-237 with 93 protons and 144 neutrons. In this equation, the alpha particle is written as helium. Beta particles are electrons, but they are ejected from the nucleus. Beta decay is more common in radioactive isotopes of lighter elements. A beta particle is formed when a neutron in the nucleus turns into a proton and an electron. The electron leaves the nucleus, and the atom transmutes to the element with 1 more proton. For example, actinium-227 with 89 protons and 148 neutrons undergoes beta decay and turns into thorium-227 with 90 protons and 147 neutrons. The beta particle is written here as an electron. The most familiar type of nuclear decay is fission. In fission, the nucleus of an atom splits into smaller nuclei, and energy is released in the form of gamma rays and subatomic particles such as neutrons. When uranium-235 undergoes fission, there are several different nuclei it can split into. 2 common products are barium and krypton. Fission is the type of radioactivity predominant in nuclear reactors and nuclear weapons. Many of the actinides result from the radioactive decay of other elements. This understanding of radioactivity was what allowed scientists to isolate and identify all the elements in the actinide series. Element number 89 on the periodic table is actinium. The atomic symbol for actinium is Ac. A radioactive metal, actinium occurs naturally in uranium ore, shown here. Actinium is named from the Greek actis, meaning ray or sunbeam. Actinium is classified as a rare earth metal in the actinide series. It lies in the periodic table 7th row, period 7. Each atom of actinium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most stable form of actinium, its nucleus has 89 positively charged protons, plus 138 uncharged neutrons. Actinium has 89 negatively charged electrons to balance its 89 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Actinium has 3 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital shell. The final electron is located in one of 5 clover-shaped 6d orbitals. The electrons in both the 7s and 6d orbitals influence how actinium interacts with other elements. Actinium occurs naturally as part of the decay chain of uranium-235. A French scientist discovered it in Paris in 1899 by extracting it from a uranium ore. Actinium is highly radioactive, so much so that the air immediately surrounding a sample of the metal will glow. Because of its radioactivity and short half-life, actinium is used only as a source of neutrons for research purposes.
Element number 90 on the periodic table is thorium. The atomic symbol for thorium is Th. A silvery white radioactive metal, pure thorium is stable in air. Thorium is named after Thor, the Scandinavian god of thunder. Thorium is classified as an element in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of thorium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of thorium, its nucleus has 90 positively charged protons, plus 142 uncharged neutrons. Thorium has 90 negatively charged electrons to balance its 90 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Thorium has 4 more electrons than radon. The first 2 electrons are found in the sphere-shaped 7s orbital shell. The remaining 2 electrons are distributed between 2 of 5 clover-shaped 6d orbitals. The electrons in both the 7s and 6d orbitals influence how thorium interacts with other elements. This gas lantern mantle is a framework of cotton gauze impregnated with thorium nitrate. Thorium is mildly radioactive, as we see with the Geiger counter. The lantern is fitted with a new mantle and then lit. The cotton ignites and burns quickly. What remains is a fragile skeleton of thorium oxide, converted from the thorium nitrate by the heat. This glows brilliantly when heated in the gas flame. The next time it is lit, the lantern will operate immediately, without the need to burn off the cotton. Radioactive thorium is a potential source of nuclear power. When bombarded with neutrons, thorium becomes uranium-233, a current nuclear fuel. Other applications for this metal include as an alloying element for magnesium, which imparts high strength. It is also used to coat tungsten wire for electronic equipment. Glass containing thorium oxide is used for high-quality camera lenses and scientific instruments.
Element number 91 on the periodic table is protactinium. The atomic symbol for protactinium is Pa. A radioactive metal, protactinium is found in trace amounts in uranium ore, shown here. Protactinium was named by adding the Greek proto, meaning first, to actinium because it precedes actinium in uranium's radioactive decay chain. Protactinium is classified as a rare earth metal in the actinide series. It lies in the periodic table 7th row, period 7. Each atom of protactinium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most stable form of protactinium, its nucleus has 91 positively charged protons, plus 140 uncharged neutrons. Protactinium has 91 negatively charged electrons to balance its 91 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Protactinium has 5 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital shell. The next 2 electrons are distributed between 2 of 7 lobe-shaped 5f orbitals. The final electron is located in 1 of 5 clover-shaped 6d orbitals. The electrons in both the 7s and 6d orbitals influence how protactinium interacts with other elements. By 1918, 2 different isotopes of protactinium had been discovered. In 1961, the United Kingdom Atomic Energy Authority extracted 125 grams of the pure element. And today, this is the main commercial source of the element. Protactinium is one of only 4 naturally occurring actinide elements. It is highly radioactive and extremely rare, so it has no uses outside of scientific research.
Element number 92 on the periodic table is uranium. The atomic symbol for uranium is U. Uranium is a radioactive heavy metal with a silvery appearance. Here, we see a depleted sample of the element. Uranium is named after the planet Uranus, which was identified shortly before the discovery of the element. Classified as a metal in the actinide series, uranium lies in the periodic table's 7th row, period 7. Each atom of uranium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of uranium, its nucleus has 92 positively charged protons, plus 146 uncharged neutrons. Uranium has 92 negatively charged electrons to balance its 92 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed in 6 orbital shells. Uranium has 6 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital. The next 3 electrons are distributed in 3 of the 7 lobe-shaped 5f orbitals. And the final electron is in 1 of the 6-level d orbitals. Only the 2 valence electrons in the 7s orbital shell influence how uranium interacts with other elements. Here we reconstruct Henri Becquerel's 1896 discovery of uranium's radioactivity. In a drawer, some coins and a metal Maltese cross are placed on top of a black light-proof plastic bag containing photographic paper. A uranium sample is placed on top of the cross. The drawer is closed and left undisturbed. After a few days, the objects are removed and the photographic paper is developed. The alpha particles emitted from the uranium have exposed the photographic paper. The metallic objects block these alpha particles, resulting in a reverse silhouette of the original cross and coins. Enriched uranium is mainly used as a fuel for nuclear weapons and nuclear reactors. In a reactor, radioactive decay generates heat, which is used to power the electrical generator. It lurks through the inner space of the world's great oceans. A deep-diving nuclear submarine, armed with more explosive power than has been detonated in all human history.
What is a submarine? A submarine is a steel tube in which we put 3,000-pound hydraulic pipes, 4,500 pounds per square inch high-pressure air. We've got 450-volt AC power, 250-volt DC power. We have fans and pumps. We arm it with the weapons of almost unimaginable destructive power. We propel it with a nuclear reactor, and then we take it out and intentionally sink it in salt water. That's not inherently safe.
It is called a boomer, a name the Navy uses for only its most powerful warships. In 1957, the Soviet Union successfully tested an intercontinental ballistic missile that could reach U.S. soil in less than 30 minutes. The U.S. responded with a nuclear triad, 3 separate defensive systems: aircraft, land-based missiles, and submarines. Together, they underwrote a policy called Mutually Assured Destruction, MAD for short. The land and air-based legs are vulnerable. Boomers are different. Their locations are a mystery, a national secret. That's what makes the underwater leg of the triad so important. They're safe from a first strike. So quiet is the modern sub that finding it would be like searching for a 20-watt light bulb hanging somewhere deep in the Atlantic Ocean.
The principal means by which one detects submarines has been acoustics. 3 types of sounds made by a submarine: the noise of the water passing over the hull. Secondly, the machinery of the submarine, the diesels or the turbines going chug, chug, chug. Third, the propeller. The cavitation, which is the formation and then breaking of minuscule bubbles around the propeller blades. Traditionally, that's been the means of detecting submarines.
Quieting the sub requires state-of-the-art, top-secret technology to mask its acoustic signature. Perhaps the most important stealth system on the sub is also the most secret: the nuclear reactor. The design is classified, and yet its function is straightforward. Uranium in the reactor is split by neutrons, releasing more neutrons and generating heat. The heat produces steam, which drives the turbines that power the boat and the generator that provides it with electricity. Before atomic power, diesel subs had to surface regularly to breathe and recharge batteries. Modern nuclear subs can go for more than 20 years without refueling. Silence, stealth, and secrecy make the submarine nearly invulnerable. Missile-firing subs are this nation's ultimate insurance policy. More than half of the U.S. nuclear arsenal rides on boomers.
I personally believe very, very strongly in the whole idea of strategic deterrence. I think that history shows it very clearly, if you look back over the last 40 or 50 years, that it's worked.
Recognize that our job is not to launch. Just the opposite. Our job is to make sure that we never find ourselves in a position where we're contemplating doing that.
My mission is actually quite simple. Be ready to launch these missiles when directed with little or no probability of anybody's interfering with that action. We do that by remaining undetected, at sea, covert, unlocated by anybody.
Element number 93 on the periodic table is neptunium. The atomic symbol for neptunium is Np. A radioactive metal, neptunium does not exist on its own naturally. Neptunium is named after the planet Neptune, continuing a pattern begun by uranium, which was named after Uranus. Neptunium is classified as a rare earth metal in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of neptunium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most stable form of neptunium, its nucleus has 93 positively charged protons, plus 144 uncharged neutrons. Neptunium has 93 negatively charged electrons to balance its 93 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Neptunium has 7 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital shell. The next 4 electrons are distributed among 4 of 7 lobe-shaped 5f orbitals. The final electron is located in 1 of 5 clover-shaped 6d orbitals. The electrons in both the 7s and 6d orbitals influence how neptunium interacts with other elements. Neptunium was discovered in 1940 by Edwin McMillan and Philip Abelson at the University of California, Berkeley. McMillan had bombarded uranium-238 with neutrons to produce the isotope uranium-239. It then underwent beta decay and became an element with 1 additional proton, element number 93. Abelson was able to chemically identify neptunium as a new element. The only current practical use for neptunium is in neutron detectors.
Element number 94 on the periodic table is plutonium. The atomic symbol for plutonium is Pu. A radioactive metal, plutonium does not exist on its own naturally. Plutonium is named after the planet Pluto, continuing a trend begun by uranium. Plutonium is classified as a rare earth metal in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of plutonium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most stable form of plutonium, its nucleus has 94 positively charged protons, plus 150 uncharged neutrons. Plutonium has 94 negatively charged electrons to balance its 94 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Plutonium has 8 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital shell. The remaining 6 electrons are distributed among 6 of 7 lobe-shaped 5f orbitals. Because the electrons in the 5f orbital are at a lower energy than the electrons in the 7s orbital, only the 2 electrons in this 7th level shell influence how plutonium interacts with other elements. Plutonium was discovered in 1941 by Glenn Seaborg, a scientist at the University of California.
We bombarded uranium with deuterons, and we found a new isotope of neptunium. And when it decayed by emitting electrons, that is increasing its atomic number, it formed a product that we could identify.
Plutonium is a primary component of nuclear weapons, and it's also used as a power source for spacecraft that are too far from the sun to use solar power.
Element Element number 95 on the periodic table is americium. The atomic symbol for americium is Am. A silvery shiny radioactive metal, americium is denser than lead. It is present as an oxide in the ionizing detector seen here, which has been removed from a smoke detector. Americium is named after the Americas. Classified as a metal in the actinide series, americium lies in the periodic table's 7th row, period 7. Each atom of americium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of americium, its nucleus has 95 positively charged protons, plus 148 uncharged neutrons. Americium has 95 negatively charged electrons to balance its 95 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed in 6 orbital shells. Americium has 9 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital. The remaining 7 electrons are distributed among the 7 lobe-shaped 5f orbitals. Since the electrons in the 5f orbital are at a lower energy than those in the 7s orbital, only the 2 valence electrons in this 7th level shell influence how americium interacts with other elements. Inside most smoke detectors is a small amount of americium oxide. The radioactivity of the americium allows a small, steady electric current to flow through the air between 2 electrodes. When smoke enters this space, it disrupts the electric current, setting off an alarm. Compared to the insignificant radiation hazard they pose, smoke detectors save many lives every year. The only current application of americium is in smoke detectors. The old saying goes, where there's smoke, there's fire. But smoke by itself is enough to kill. In fact, the #1 cause of fire-related deaths is smoke inhalation. Smoke from a fire causes problems both by taking away oxygen necessary for breathing and by producing poisonous gases. Some substances damage the lungs, while others, such as carbon monoxide, interfere on a cellular level. The best way to combat smoke inhalation is by prevention. And smoke detectors provide a crucial early warning in the advent of fire. In the early 1940s, a Swiss inventor named Ernst Maly developed the first smoke detector to use an electric current across an ionized space. Then, in the 1960s, an American scientist named Glenn Seaborg patented a method for producing americium in plutonium reactors. The 2 processes finally came together in the early 1970s, when several different patents were issued for ionizing smoke detectors using a radioactive substance. Today, americium is a necessary component of most ionizing smoke detectors. Americium smoke detectors use a combination of low-level radioactivity and electricity to provide a vital warning system against smoke and fire. The americium in smoke detectors undergoes alpha decay, so it is constantly giving off alpha particles. These particles pose no health hazard and actually save lives in the event of a fire. The alpha particles are positively charged, and by interacting with other atoms in the air, they create a small area of ions within the smoke detector. A small amount of electricity is able to travel across this ionized air. Smoke is the result of incomplete combustion. It consists of fine particles of carbon or soot suspended in a mixture of air and hot gases. When smoke is present, the soot absorbs the alpha particles and ions are not formed. Without the ions in the air, the electricity cannot cross the space in the detector and the current stops. The lack of current is what sets off the alarm. If the smoke dissipates, the ionization is resumed and the alarm stops. Smoke detectors are sensitive enough to sound the alarm several minutes before a blaze becomes out of control. The time provided by americium-based smoke detectors is absolutely vital to people who might otherwise be trapped by fire.
Element number 96 on the periodic table is curium. The atomic symbol for curium is Cm. Curium is named after Marie and Pierre Curie, the couple who discovered the elements radium and polonium. A radioactive metal, curium does not exist on Earth naturally. Curium is classified as a rare earth metal in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of curium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most stable form of curium, its nucleus has 96 positively charged protons, plus 151 uncharged neutrons. Curium has 96 negatively charged electrons to balance its 96 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Curium has 10 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital shell. The next 7 electrons are distributed among 7 lobe-shaped 5f orbitals. The final electron is located in one of 5 clover-shaped 6d orbitals. The electrons in both the 7s and 6d orbitals influence how curium interacts with other elements. Pierre and Marie Curie shared the 1903 Nobel Prize in Physics in recognition of their research in radiation. Pierre became a professor at the Sorbonne in Paris in 1904, and he died 2 years later. After Pierre's death, Marie took her husband's position and became the first female professor at the Sorbonne. She won a second Nobel Prize in Physics in 1911, and during World War I, she pioneered the use of X-rays in medicine. Marie paid a heavy price for her scientific research. She died of leukemia in 1934 as a result of her exposure to intense radiation.
Element number 97 on the periodic table is berkelium. The atomic symbol for berkelium is Bk. A silvery radioactive metal, berkelium does not exist naturally. Berkelium is named after the town of Berkeley, California, where the element was first manufactured. Berkelium is classified as an element in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of berkelium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most stable form of berkelium, its nucleus has 97 positively charged protons, plus 150 uncharged neutrons. Berkelium has 97 negatively charged electrons to balance its 97 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Berkelium has 11 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital shell. The remaining 9 electrons are distributed among 7 lobe-shaped 5f orbitals. Because the electrons in the 5f orbital are at a lower energy than the electrons in the 7s orbital, only the 2 electrons in this 7th level shell influence how berkelium interacts with other elements. Berkelium is named after Berkeley, California, the location of the Lawrence Radiation Laboratory at the University of California. Berkelium was first created there in December 1949. It was made by bombarding an americium target with helium ions for an extended length of time.
Element number 98 on the periodic table is californium. The atomic symbol for californium is Cf. Californium has never been seen with the naked eye. Like all elements heavier than uranium, it is radioactive and does not exist naturally on Earth. Californium is named after the state of California, where it was first made. Californium is classified as a metal in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of californium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most stable form of californium, its nucleus has 98 positively charged protons, plus 153 uncharged neutrons. Californium has 98 negatively charged electrons to balance its 98 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Californium has 12 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital shell. The next 10 electrons are distributed among 7 lobe-shaped 5f orbitals. Since the 10 electrons in the 5f orbital are at a lower energy than those in the 7s orbital, only the 2 valence electrons in the 7th level shell influence how californium interacts with other elements. Californium was first made in 1950 by a team of scientists at the laboratory at Berkeley, California. They bombarded curium with helium ions and made just enough californium to identify it as a new element. There are 8 known isotopes of californium. Californium is a good source of neutrons, the basis for most of its uses. It is used for geological analysis in gold mining and oil wells, and for the treatment of cervical cancer. Cancer is a serious disease that afflicts people from all walks of life. But many patients diagnosed with cancer have several options for treatment and go on to live long, healthy lives. This was not always the case. Up until the beginning of the 20th century, the only treatment was surgery, but it was often dangerous and could prove as deadly as the disease.
Prior to 1955, cancer was thought of as equal to death. The word cancer was equated with death.
So the doctor would tell the patient, well, there seems to be a little lump or there's a growth here and we'll take care of it. And, they would proceed to treat the person, oftentimes without ever telling them that they had cancer.
By the early 1950s, scientists had begun developing a clear understanding of radiation and its effect on human cells. They discovered that high doses of focused radiation improved the condition of people with certain types of skin cancer and other tumors that were beyond the reach of surgery. But early X-ray radiation therapy was not a miracle cure. It had unpleasant side effects and occasionally caused other types of cancer.
A lot of the long-term survivors, due to the amount of radiation that we had back in the leukemia days, developed breast cancer as a secondary deal.
And some cancers wouldn't even respond to treatment. To reduce side effects and improve response rates, researchers began experimenting with an internal radiation source. In the 1970s, clinical trials at the University of Kentucky began using californium-252 brachytherapy to treat cervical cancer. Brachytherapy is a method that involves placing a radiation source close to or inside a tumor itself. Its proximity to the cancer cells allows a higher dose of radiation to be delivered, making less of an impact on nearby healthy cells compared to external radiation. The high-energy neutron radiation of California has proved especially effective in treating cancers that do not respond to other types of radiation therapy and cancers in advanced stages of development. Regular screening has significantly reduced the number of cervical cancer cases requiring intense radiotherapy treatment. But the success of Californium brachytherapy suggests great potential in treating other types of cancer and provides continuing hope to women diagnosed with cervical cancer.
Element number 99 on the periodic table is einsteinium. The atomic symbol for einsteinium is Es. Einsteinium is named in honor of Albert Einstein, who did extensive work in particle physics. A radioactive metal, einsteinium does not exist naturally. Einsteinium is classified as an element in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of einsteinium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most stable form of einsteinium, its nucleus has 99 positively charged protons, plus 153 uncharged neutrons. Einsteinium has 99 negatively charged electrons to balance its 99 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Einsteinium has 13 more electrons than radon. The first 2 electrons are found in the spherical 7s orbital shell. The next 11 electrons are distributed among 7 lobe-shaped 5f orbitals. Since the electrons in the 5f orbitals are at a lower energy than those in the 7s orbital, only the 2 valence electrons in this 7th level shell influence how einsteinium interacts with other elements. Einsteinium was discovered in the debris of the first thermonuclear test explosion, which took place on a Pacific atoll in November of 1952. Scientists produce einsteinium by bombarding plutonium with neutrons. Because it has no known applications, it is only created for scientific research. The scientists who discovered einsteinium named the element after the renowned physicist and mathematician Albert Einstein, whose work paved the way for the development of nuclear power.
Element number 100 on the periodic table is fermium. The atomic symbol for fermium is Fm. Fermium is named after Enrico Fermi, who won the Nobel Prize for Physics in 1938. Like all elements heavier than uranium, fermium is a radioactive metal that does not exist naturally on Earth. Fermium is classified as a metal in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of fermium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most stable form of fermium, its nucleus has 100 positively charged protons, plus 157 uncharged neutrons. Fermium has 100 negatively charged electrons to balance its 100 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Fermium has 14 more electrons than radon. The first 2 electrons fill the sphere-shaped 7s orbital. The remaining 12 electrons are found in 7 lobe-shaped 5f orbitals. Since the electrons in the 5f orbital are at a lower energy than those in the 7s orbital, only the 2 valence electrons in this 7th level shell influence how fermium interacts with other elements. Scientists at the University of California discovered fermium in 1952. They found it in the fallout material of the first thermonuclear test explosion, codenamed Mike. Enrico Fermi was the first person to create a self-sustaining nuclear fission reaction. He applied his knowledge of nuclear physics as a participant in the Manhattan Project, which designed the first atomic bomb. Every year, to recognize achievement in nuclear science, the United States Department of Energy gives the Enrico Fermi Award, named in his honor.
Element number 101 on the periodic table is mendelevium. The atomic symbol for mendelevium is Md. Mendelevium is named after Dmitry Mendeleev, who developed the periodic table. Like all elements heavier than uranium, mendelevium is a radioactive metal that does not exist naturally on Earth. Mendelevium is classified as a metal in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of mendelevium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of mendelevium, its nucleus has 101 positively charged protons, plus 157 uncharged neutrons. Mendelevium has 101 negatively charged electrons to balance its 101 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Mendelevium has 15 more electrons than radon. The first 2 electrons fill the sphere-shaped 7s orbital. The remaining 13 electrons are found in 7 lobe-shaped 5f orbitals. Since the electrons in the 5f orbital are at a lower energy than those in the 7s orbital, only the 2 valence electrons in this 7th level shell influence how mendelevium interacts with other elements. Mendelevium was first made in 1955 by a team of scientists at the University of California, Berkeley. Their night-long experiment produced 17 atoms of the element with a half-life of 78 minutes. Scientists have since produced millions of mendelevium atoms, enough to study the element and measure some of its properties. Dmitry Mendeleev, for whom mendelevium is named, discovered the periodic law. Using his findings, Mendeleev created the periodic table, which was revolutionary in that it included gaps and predictions for elements that had not yet been discovered. Scientists have since filled in the gaps and made some minor changes to the organization of the modern table, but Mendeleev's basic structure can still be seen.
Element number 102 on the periodic table is nobelium. The atomic symbol for nobelium is No. Nobelium is named after Alfred Nobel, the Swedish chemist who founded the Nobel Prize. Like all elements heavier than uranium, nobelium is a radioactive metal that does not exist naturally on Earth. Nobelium is classified as a metal in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of nobelium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the longest-lived form of nobelium, its nucleus has 102 positively charged protons, plus 157 uncharged neutrons. Nobelium has 102 negatively charged electrons to balance its 102 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Nobelium has 16 more electrons than radon. The first 2 electrons fill the sphere-shaped 7s orbital. The remaining 14 electrons fill 7 lobe-shaped 5f orbitals. Since the electrons in the 5f orbital are at a lower energy than those in the 7s orbital, Only the two valence electrons in this seventh level shell influence how nobelium interacts with other elements. In 1957, a group of scientists at the Nobel Institute of Physics in Stockholm claimed to have discovered element 102, but their results could not be verified. However, they named the element nobelium, and the name was kept when scientists at the University of California at Berkeley finally identified the element in 1958. Alfred Nobel was a Swedish chemist who made a fortune as the inventor of TNT. In his will, Nobel put the majority of his fortune into a trust fund to establish awards for discoveries that led to the betterment of mankind, today known as the Nobel Prize.
Element number 103 on the periodic table is lawrencium. The atomic symbol for lawrencium is Lr. Lawrencium is named after Ernest Lawrence, the inventor of the cyclotron. Like all elements heavier than uranium, lawrencium is a radioactive metal that does not exist naturally on Earth. Lawrencium is classified as a metal in the actinide series. It lies in the periodic table's 7th row, period 7. Each atom of lawrencium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the longest-lived form of lawrencium, its nucleus has 103 positively charged protons, plus 159 uncharged neutrons. Lawrencium has 103 negatively charged electrons to balance its 103 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Lawrencium has 17 more electrons than radon. The first 2 electrons fill the sphere-shaped 7s orbital. The next 14 electrons fill 7 lobe-shaped 5f orbitals. The final electron is found in one of 5 clover-shaped 6d orbitals. The electrons in both the 7s and 6d orbitals influence how lawrencium interacts with other elements. Element 103 was first made in 1961 at the University of California at Berkeley. Scientists in Russia confirmed the results, and the Berkeley scientists named the element lawrencium. Many isotopes of the element have a half-life of less than a minute. Ernest Lawrence was a physics professor at the University of California at Berkeley. He created the first particle accelerator, called the cyclotron. With the cyclotron, scientists were able to create previously unknown heavy elements such as berkelium and californium. For his invention, Lawrence received the Nobel Prize for Physics in 1939 and the Fermi Award from the United States Department of Energy in 1957.